We talked about a couple of practical applications of divergence theorem and the Stokes theorem, basically to remind you what that is, right? So the divergence theorem is trying to relate a closed surface flux integral to a triple integral over the volume of the divergence of that vector field. And the Stokes theorem is trying to relate a circulation, so a closed loop line integral to the surface of the curl of that integral. So this is the flux integral of the curl of that circulation of that closed loop. So we talked about practical applications of it. So I want to talk about how about conceptually, it can be really powerful as well. So, for example, imagine you have a vector field that represents like the fluid, and you have like a fishnet, right? So imagine this is this is an open circle over here, and it's covered by like a surface. It's hard to imagine, but kind of imagine this is like a fishnet, right? So this is all around, wrapping it around, and this is the surface of that. So let me call this S fishnet. Okay, right. So one interesting thing you might be interested in is, well, there's a vector field. Imagine there's a vector field through here. So there might be, you might want to find out how much fish you can catch, assuming if the fishes are just following the fluid flow, right? So they're literally just whatever the vector velocity vector of the fluid is. They basically, all the fish have fallen asleep, and they just follow whatever the vector field of the fluid is. All right. So by calculating how much flux, how much of these vectors go through here, you kind of measure how much fish are going to be caught in this once you add up all the surface, right? So what you want is, you might want to calculate, well, the open surface. So this is an open surface, right? Because of the open opening over there. So you would want to calculate the flux, right? So this is the flux integral. You want to calculate the flux through the fishnet, right? Like this. Now, it's very difficult to parameterize the fishnet. This is a surface, right? This surface, imagine parameterizing this with, trying to parameterize this with UV, right? So with two parameters, like that. How difficult would that be? Well, we can make use of either the divergence theorem or the Stokes theorem. Both would actually give you a hand in this. So I mentioned this in the lecture, but kind of used the wrong equation there. So let's think about it. So the idea is, let's introduce a new surface to close this up. Okay, so this, let's say, is the S disk, is the closing bit. Well, then this fishnet is equals to the total integral of basically S fishnet plus, or union with, the disk, right? So I can, is this equal to this? Well, no, I'm calculating extra bits of flux that is going through here that I don't want. So let's subtract away the flux through the disk of the vector field. Okay, so I can do that. And now this part is the same as this part, right? So I'm now doing a closed surface, a fully closed surface flux integral, and that's equals to the divergence. And now I can invoke the idea of a divergence and replace that, right, with the divergence of the vector field throughout the volume of the fishnet, right? The interior of the fishnet, volume of the fishnet, and as disk, this stays the same. Now, okay, so if there are two scenarios here, if the vector field is divergence free, or if the vector field is not divergence free, right? So this is div f equals to 0, right? So if that's true, and this is a lot of times vector fields would satisfy this, because this is actually translates to the incompressibility of the fluid. If the vector field is incompressible, it means that there cannot be any sources anywhere. So the divergence has to be 0 at every point. So that means that if there's a local point over here, any fluid that goes in must come out. If this is not 0, it means the fluid is possibly compressible because it can be more going in and less coming out of each point, right? If this is negative, so that means more going into a certain point than coming out. So you have sort of a sink at a certain point. Or if this is larger than 0, so less goes in and suddenly a lot coming out. Fluids normally do not do that unless there's a sink, right? So more goes in and less come out, or a source where nothing goes in or very little go in and suddenly a lot of things comes out, like this. So there's a source. So imagine there's no sink and sources within this area. So usually the divergence should be 0 within this area. All right. So if that is true, then this is 0. And now you just need to calculate this. So what is this? This is parametrizing the disk over here, and it's a much more easier task. So you have translated this to negative of this. Conceptually, this makes sense as well. If you don't have any sources of sink over here, then any flux through this surface should just be negative of the flux through here. That kind of makes sense as well. And if you so this is one way to use the divergence theorem. But even if you have a case where the divergence is not free, it's not 0, this is a relatively easier integral to do than to parametrize this, because remember, dealing with the ds vector involves first parametrizing it and then calculating a cross product, du, dv, and then also deciding whether it's a plus or minus sign over there. So a lot of effort goes into this, a certain amount of effort goes into this, some degree of effort going into this. Okay. Now, all of this can also be interpreted with the Stokes theorem. We can do exactly the same argument, or very similar argument. So if you have back to this fishnet, right? And I want to calculate this fishnet surface f dot ds. So I want to calculate the flux through the fishnet. Now we can check. We can use the Stokes theorem. So what was the Stokes theorem? The Stokes theorem says that the circulation of any vector field over a closed loop, right, is equals to the open surface of the curl of the flux of the curl. Okay, so if I have this, now this is a surface integral. So in order to apply this, the only way to be able to apply the Stokes theorem is if I can write this vector field f over here as a curl of something, right? Now, this is true if f is divergence free. So if this is 0, then remember there's an identity saying the dot product of the curl is always 0, right? So if this is true, then I can basically write, so there should exist another vector field, let's call it A, such that f is equals to the curl of A. Okay. So once again, this is possible if this is possible. All right, so let's deal with this case first, because we talked about fluids. Often this is true for fluids. Okay, so if that is true, then I can write this as curl of A, which is in physics called the vector potential of the vector field. All right. So if this is true, I can write that. Now I can use the Stokes theorem and write it as C A D R. Okay, so what that means is I am now calculating what is the effect of A around this opening over here, because this is the boundary of this surface, right? If you have a fishnet, where's the boundary, right? Remember, this has to be the boundary of whatever that is. Well, this is the boundary. Okay. Now, this boundary shares the same boundary as this surface. Okay, so if we call this surface as disk, as fishnet, notice both the red surface and the white surface shares the same boundary C. So we can also rewrite that as using so this involves Stoke's theorem, and I can rewrite this as this, but the disk. So this is using sort of inverting the inverse of the Stoke's theorem. Okay, so you can go backwards, and that, of course, is equals to F again. Okay, like that. So now you can see that if I wanted to calculate this, we talked about it's very difficult to parameterize this, somewhat annoying to parameterize this, but also very difficult and very annoying to parameterize this. So there's a lot of annoyance there, but via Stoke's theorem, it tells me that all I need to do is calculate the parameterize the disk, which is easy because it's a flat surface. You can use either Cartesian or polar coordinates, both would work, and that would be easy to calculate, that would be easy to calculate, right? Of course, this is the same result as what we had with the divergence theorem. You see that the fishnet is equals to the negative of that. In case you're wondering why there's a negative, that's because how we define the ds. When we are invoking a over here the full complete closed surface, this ds essentially is opposite of this ds, because here the ds by convention over a closed surface should be defined as pointing outwards from the interior, so it's pointing in this case to the left of the screen. Over here we are going through the same orientation, so if the C is around the same orientation, so if for the fishnet surface, if the ds is pointing in one way, the ds is also pointing in the other way. This is just about which way this curve is going around. So in case you're wondering where's the negative sign, that's the reason. This ds is pointing this way, and it's different from this ds, where by convention it's the if this is the same orientation of the curve, then these would sort of be pointing in a similar direction. Okay. All right, so you see conceptually, we saw practical uses of this is when one side is difficult to calculate, you try to calculate the other side. And we also see a conceptual application is sometimes when you just want to calculate an open surface, right? Because if you look at these two theorems, none of them teaches you how to calculate open surface of a vector field. This tells you how to calculate open surface, but this is not simply a vector field. But the concept kind of allows you to relate this to something easier to calculate. And like we said, with the catching fish example, kind of makes sense. If you want to find out all the flow or the flux through this surface, it's the same as calculating all the flux from here, given that the fluid has no sources or sinks in the middle. If there's a sink, of course, what goes through here not necessarily come out, or if there's a source, a positive divergence over here, what goes in here doesn't necessarily equate to what goes out. There will be more going out through here, right? But if the divergence is 0, which translates to incompressibility of fluids, then it means that anything at every single point, whatever goes in would also come out. So calculating all the flux through this surface is the same as the flux through this complicated surface. So conceptually, very, very powerful. Okay, hopefully this makes sense, and let me know if you have any questions. Have a good day.